Latency in the previous years has had only a single speaker track, and so you were forced to listen to me, whereas this time you're making a choice to be here. So thank you for making that choice, and just remember, whatever happens next, you chose to be here. So it's really your fault. So, the galaxy is in turmoil. The relentless churn of JavaScript frameworks and the growing threat of supply chain attacks have left the developer alliance fragmented and weary. Desperate for a solution, the alliance searches for a new hope, a way to restore balance to the chaos of cloud-native application development. In this dark hour, an old hero rises from the shadows of the past. Once exiled from the browser, the JVM returns, reborn anew as WebAssembly. But will our new hero be enough to save the day? Or will the promise of write once, run anywhere ring hollow once more? Act 1, the rise of the old republic. The keynote provides no way to skip animations, so we're just gonna have to wait for the scroll to finish. There we go, all right. So to start our story, we need a little bit of historical context because some of the people in this room were born after 9/11. So we're gonna take a bit of a trip back to the internet in the early 90s, 30 years ago, which is hard to imagine. So if you were using the internet back then, this might look painfully familiar. You know, graphic design is my passion, really ruled the internet back in those days. And the internet was really was fairly limited in scope back then. It was like mostly static documents sort of like hyperlinked together, right, into this kind of like network of information. But the amount of interactivity you could achieve on the web was really restricted to basic forms. So like you can see Google here with its like search input. That was kind of like the limit of interactivity in the early days. And so chafing against that, there was kind of a Cambrian explosion of plugins to the browser or extensions to the browser to try and achieve that interactivity. So this is the kind of timeline we'll be exploring today, but initially we're just focused on this green section at the beginning here. So Netscape 2 saw JavaScript being delivered in 1995. Infamously only developed in 10 days, and we're still living with the legacy of that now. So glad that they put that amount of thought into that platform. And then soon after, with the popularity of Java, we saw the advent of Java applets, right? And then Adobe Flash and sort of ActiveX soon after, with all of these vendors trying to make their plugin the way to do interactive web applications beyond what was capable with HTML and JavaScript at the time. And so you might also remember wonderful prompts like this. So this is an example of the prompt you would get when you visited a website that used ActiveX. And it's warning you here because like the security of these early plugins like ActiveX and Java applets were an absolute nightmare, right? Like ActiveX, at least initially, just had access to your entire file system. It could do like all sorts of dangerous stuff. And so it's like, are you really sure you trust this website? And sandboxing was attempted to be added later, but it wasn't very great, and it was a constant source of security exploits. They were also just like really slow and take a long time to download. And when you built a web application with these, you weren't really building a web application. You were building a website with a hole punched in it, and then like a separate app in that hole, right? There was no real interactivity between the outside HTML and the inner plugin and vice versa. And there were attempts to solve that later, but it never really took off. And if your users didn't have the plugins installed, you'd get all these wonderful error messages. But despite all of these problems, they really reigned supreme for a very long time. And so that brings us to Act 2, which is the fall of the old republic. And I think one man can really be said to be responsible for the fall of Java, or Java applets and Flash. And that is Steve Jobs with the introduction of the iPhone. I don't know if you remember, the iPhone infamously shipped without Flash support. And for a little context, like Flash was installed on 95% of browsers at the time, right? Like if you wanted to deliver interactive multimedia experiences via the web, you did it via Flash. And the iPhone and Steve Jobs comes out and is like, no, we're not doing Flash anymore. You know, in typical Apple fashion, just completely potentially killing off an entire industry. And so now we're at the sort of middle part of our timeline. And it was actually kind of funny. Android, there was a big distinguisher in the early days of Android where they were like, well, we support Flash, so you should come and use Android. I remember friends of mine being like, oh, you can't even use Flash on your iPhone. But then shortly after, in 2012, Android also drops support for Flash because it's so bad, it performs so badly on like mobile processors. And around the same time, we see HTML5 starting to take the stage. So it was introduced in 2008, but didn't receive full recommended status by W3C until 2014. But you can already see the shifting winds as like people start interacting with the internet more and more through their phones, and the app store is the way that they start consuming things more and more, you start to see the death. I mean, Silverlight, actually I forgot to put it on here, but Microsoft only worked on Silverlight for like 3 years before dropping it. And so you can see Java applets die also in 2013. So that brings us to Act 3, the rise of WebAssembly. And it starts with some pretty humble beginnings. So in 2013, Firefox announced ASM.js. I don't know if people in this room are really familiar with that. But they did so with a fairly spectacular demo of porting the Unreal Engine 3 to the browser. And like that was just completely unheard of at the time, right? Like it seems kind of quaint by today's standards, but the ability to ship a real-time 3D engine running entirely just in JavaScript and in the browser was groundbreaking at the time. And they did so, the readability on that's awful. They did so by doing a whole bunch of tricks to JavaScript to trick the just-in-time compiler to perform optimizations that it normally wouldn't. So you can see some of these math operations here are being sort of bitwise XORed with like 0, and that indicates to the just-in-time compiler that it's a 32-bit integer and not like a double or some other kind of dynamic type. And so that's how they were really able to achieve that sort of almost native performance. They were able to take C and C++ code and compile it through LLVM into ASM.js, which was this weird kind of dialect of JavaScript that no one would write by hand because it contained all these like tricks. But it had a number of problems, and one of the biggest ones was the files were enormous once they got compiled into ASM.js. And then that leads into the next problem, which is that JavaScript is actually relatively slow and difficult to parse based on its syntax. So large files plus slow parsing means really, really slow load times. And ultimately, at the end of the day, it was still only capable of what JS was capable of. So there's actually no way, even with all those JIT tricks, to get an int64. Like the bitwise operands give you an int32. It's actually impossible in JS to get an int64, right? And then other things missing, like unaligned loads and stuff like that. So, but ASM.js as an experiment did prove that the browsers, like the JavaScript VM, was capable of near-native performance. And so WASM was announced to try and fix all of those problems with ASM.js, right? And make it much easier to target. So this is an example of the textual representation of WebAssembly. It kind of looks like this weird hybrid between Lisp and assembly, if you've ever read assembly before. So the first weird thing is that it's got structure to it, right? So it's actually based on an abstract syntax tree rather than just kind of being like a string of instructions like traditional assembly. And that becomes important for parsing and validation. It also has structured control flows, so you can see it's actually got a loop construct in there as well. Like you would never see that in assembly, right? Like you always see just jump ifs in assembly. It's also like strongly typed. Well, actually, funnily enough, it only actually supports 4 core types, which are the 32-bit and 64-bit variants of floats and integers. So if you want a string, you have to kind of bring your own representation of that. Usually as 2 integers, like one as a pointer into memory and the other as the length. But all other high-level types have to be built on top of just like these 4 core kind of numbers. But that strong typing is what really enables the speed of WebAssembly. It's stack. I'm not going to get into why it's stack-based. It's also binary encoded, so it's very fast to download and parse. And it's also streamable. The engine can start working on evaluating the WebAssembly as it's coming in. It doesn't need to wait for the whole thing to come in before it can start working. And so essentially the pitch of WebAssembly is it's a binary instruction format with a stack-based virtual machine. And that sounds awfully familiar to a technology that was already in the browser, which was the JVM. So it's like, why did we go invent a new VM? Why can't we just use the JVM? And so that brings us to our first side quest. So I only have 25 minutes, and so as much as I would love to dive into the juicy, crunchy details of this, don't have time for it. This is an excellent 90-minute talk that goes into like real into detail about the differences, and so I highly encourage you to check this out. But at a high level, the main problems were like Java is like a proprietary virtual machine. It's not like an open web standard. It's kind of standardized outside of that process. And so getting it into browsers is actually kind of non-trivial. It has a really large API surface. Like it specifically supports the JDK API as part of like the VM. And it's also very opinionated specifically for Java, so there's no way to opt out of the garbage collection, for example. And it also bakes concepts of like object-oriented programming into the VM itself. So it's good for the JVM to be opinionated for Java, not so good as a compilation target for other languages with different semantics. And so that kind of brings us to the last part of our timeline, which is the sort of meteoric rise of WASM. And so the features of the WebAssembly virtual machine, of this super lightweight, performant, and heavily sandboxed virtual machine, started to catch the attention of people outside that were interested in using it outside of the browser, right? And that's when the Bytecode Alliance forms and the WASI standardization, so the WebAssembly System Interface begins, and the journey of WebAssembly breaking out of the browser. And so also finally, Flash was the last one to die in 2020, although I've got it as 2021 on the timeline. So just like to take a moment to in memoriam for Flash. Like it hung on the longest of all of our plugins, but unfortunately is also now dead. So what are some industry uses of WASM that are happening today? ChatGPT really didn't want to generate this image because of child slavery being against its content policy, until I was like, well, it's Victorian, so it's historically accurate. So one of the more famous examples of a company built around WebAssembly is Figma, which really needed the performance of WebAssembly to deliver the like Adobe Illustrator-like experience in the browser. Secondly is Autodesk. They were able to ship AutoCAD to the browser, which was completely unthinkable beforehand. Also, like iCloud, when they moved their iWork productivity suite, so like their version of Microsoft Office, to the browser, they were able to take entire sections of their C++ and Objective-C code bases and compile them directly into WebAssembly rather than needing to rewrite it. So they were able to reuse large chunks of their code base, allowing them to deliver that a lot faster than they would be otherwise. Another one is Polkadot. I'm kind of loath to talk about it because I really hate blockchain, but Polkadot is using the WebAssembly virtual machine as their smart contracting virtual machine instead of dealing with the mess that is the Ethereum virtual machine, if anyone out there is familiar with all the problems that come with Ethereum. And then lastly, for the data scientists out there, Jupyter Notebooks are actually working on this project called Jupyter Lite, where instead of needing a server behind your notebook, it can compile and run entirely within the browser. So like you no longer need to be provisioning these machines for these notebooks. They can just run entirely at almost native speed in the browser itself. And so that brings us to like trying to move beyond the browser, right? So those were all browser-based applications, but like how has WebAssembly grown outside of the browser? So on the server side, I spoke last year quite a lot about Cloudflare workers. So they've supported WebAssembly since 2018, I think it was. And enables all sorts of like interesting compute at the edge, including they're really pushing doing like large language model inference on the edge using WebAssembly. We also have Shopify. So Shopify lets users upload their own code targeting WebAssembly to apply custom discount rules in their shops, right? So Shopify as a platform is allowing their users to run untrusted code in their servers, and they're able to do that efficiently, cost-effectively, and securely by leveraging the WebAssembly virtual machine, which has all of those properties. I'm going to speak a little bit more about SpaceTimeDB later, but one of the really cool things they're doing is stored procedures and user-defined functions using WebAssembly on the database, and potentially eliminating the need for having your own backend entirely, which is pretty cool. And then lastly, Lucet, which is the Fastify WASM runtime, they claim the ability to run tens of thousands of WebAssembly virtual machines in a single thread, right, with just like 30 microsecond startup time. If you compare that to like Lambda, right, you're usually measuring startup times in milliseconds or even seconds. 30 microseconds to start up a new context, tens of thousands of them in the same thread, with each one only taking up a few kilobytes of memory. So that's the kind of insane sandbox performance that you can get, that you can leverage out of the virtual machine. There is kind of like one small problem, which is that part of WebAssembly's security model is that it doesn't actually do anything. Like it can only do pure computations, right? Like it can do math, basically. It can't actually write to disk or to network or print anything. And the way you get around that, if I can just skip back for a second, you see in the top section, you can see it importing functions from the host, and that's the only way that WebAssembly can actually do stuff, is the host has to give it like a function pointer, being like, call this if you want to do some kind of side effect. And so the result of that is that every runtime or every WASM host kind of is defining their own interface for how to achieve this, right? And so you can't take a WebAssembly module written for Cloudflare and move it over to Fastify. It doesn't require much reworking to do that, but you can't just like take it and move it. And so that's why the WebAssembly System Interface exists. And this is an attempt to standardize what these interfaces look like for various processes. So be that HTTP or logging or threads or like random number generation even, like the WebAssembly virtual machine is entirely deterministic, so if you want a non-deterministic behavior, that's technically a side effect that you need to import. But then also as part of the WebAssembly system interface work, you can now compose modules of different languages together, right? And they each receive their own sandboxing. And so this is where it gets really interesting for supply chain attacks. Because right now, so that QR code leads to a blog post announcing WASI. And so the following images are all taken from that blog post. So traditionally, application security, even with something like Dino, where you can give fine-grained permissions, like you can only read this file or like this network socket or whatever, you're still giving that permission transitively to all of your dependencies. So not like the direct dependencies that you've imported, but also their dependencies and their dependencies, right? And we know with like NPM and stuff like that, like you import like a single thing and it imports like 10,000 NPM modules, right? And so if you're like, you can read this file, now every one of those modules can read a file. But WebAssembly opens up this like new paradigm where every single dependency can receive its own micro sandbox, right? And so one of the examples they go through in the blog post is there was this crypto wallet, Agama, that was attacked last year, and over $150 million of crypto was stolen. And the way they did it was essentially infecting one of the transitive dependencies of the app and waiting for the new thing to be released. And then that was able to go and steal the seeds for the wallets directly out of the application and send those off. And that was possible because like the application itself, A, was operating under shared memory, and B, was allowed to talk over the network. Whereas under WebAssembly, every dependency only gets the exact functionality that it needs, and they all have isolated memory. So in the event that a transitive dependency is corrupted, it can't talk to the network, and it can't even read the memory of the other process, right, or of the other microprocess. And so we're getting towards a world where you can potentially have these polyglot applications where every dependency is potentially written in a different language. So that brings us to, I think, the near future. So this isn't necessarily what's possible right now, but I think is going to become possible in 5 to 10 years now. There's this project called WASM Cloud, which is being worked on by the Cloud Native Computing Foundation, the same guys who maintain Kubernetes and other projects like that. And now that you have all of your apps componentized, well, actually, maybe a better question is, who here uses microservices? Yeah, okay, sweet. Who thinks that they could go in and shut off one of their microservices and not have their entire app collapse? Okay, I can see 2 hands. Okay, yeah, but at least for me, every organization I've ever worked for, it's not really microservices, it's a distributed monolith, right? Like you have, the reason you have microservices is organizational, not technical, right? It's Conway's law in action, which is that a system's architecture will reflect the organization's communication structure, right? So the reason you have 6 microservices is because you have 6 teams, right? Or potentially even more. But under WASM, or under the component model, like your services are already talking to each other over the network via these well-defined interfaces. So why not deploy components instead of containers and then have the runtime compose those components together, right? And replace all of those network calls of APIs with direct function calls, right? There's no reason that because like you don't actually have you don't actually have microservices. You've got a single service, a distributed monolith, and the network calls are like the boundaries between your components, right? So why not just like collapse them all together into like a single monolith again, right? Because that's what you really have, most of the time at least. And so I think this could potentially represent the death by microservices, right? Because microservices incur this enormous operational overhead, and most of the time you don't need it for a technical reason, you need it for an organizational reason. So if that's true of your org, if you can't go into your organization and kill one of your microservices and not have your entire platform fall over, then maybe you should be thinking about something like this, the fact that you actually do have a monolith, just separated by network calls. And so that leads us to even stranger ideas, right? Where now we can have your compute mesh is like cloud, and then also like edge locations, and then also even potentially user edge devices, right? And your workloads and their components can be distributed like across that whole thing, right? So maybe you're still using Kubernetes on your server to sort of run WASM Cloud on top of that, but then WASM Cloud can potentially be deploying those workloads even to user devices, right? And so I'm about to show you a really inflammatory tweet, but it's made by the creator of Docker. So if anyone was going to claim this next statement, like surely the creator of Docker has a right to, which is that if WASM and WASI existed in 2008, we wouldn't have created Docker. And that's the creator of Docker saying that. So it's a pretty inflammatory statement. This was made back in 2019 before WASI had made the progress that it has right now. But he was like, yeah, if this technology existed and was mature back in 2008, we wouldn't have created Docker. That's kind of crazy. And so in these last few minutes, I'd like to talk about another concept real briefly, which is data gravity, which is generally the concept that it's easier to move your compute to your data than it is to move your data to your compute, right? Data is kind of like heavy in a gravitational sense, and it attracts more data to it, and it kind of attracts compute to it as well. But usually what right now is we have this strong separation between compute and data, and the compute that we do have with our data is entirely available usually through SQL or some other kind of like relatively limited scripting language. And so I met these guys in San Francisco when I was there last week called SpacetimeDB, and they started off trying to make an MMO, but then realized that the backend technology they were building for it was kind of more interesting than the game that they were working on. And so they made SpacetimeDB, and their kind of realization is kind of similar to what I was talking about with WASM Cloud, which is like, why not just move your compute to where your data is, right? Like, why do you have a separate backend and a separate database if you can run your code on the database where it has direct access to the data? Like, why not just run it there? Why not just get, like, why do you have an API? Like, why do you have a backend when you can just be running all of your business logic, like, in the database, in a WebAssembly VM, basically, right? And that's exactly what they're doing here, right? So the user runs a query against the database and essentially subscribes to a like running changelog of that. And then they're able to execute mutations on that by calling what they call reducers, which all run in WebAssembly VMs on the database. So like you don't have your own backend, you just have this database, and all of your application code lives in the database. And I think that's pretty cool. So should you run away from this talk right now and go back to your organization and be like, we need to be using WASM? And the answer may be yes, if you really need the speed improvements in the browser, or if you need the lightweight sandboxing, so like Shopify's use case, where you need to be trying to run untrusted code and you need some kind of lightweight sandbox. Or if you need a virtual machine that you need to target with many different languages, right? That being said, though, I heard this concept a few years ago, and I don't know where it's from, so apologies for not being able to attribute it properly. But it was like every project comes with like 3 innovation tokens. And you get to spend those on different technologies for a project. And I think if this is your first foray into WebAssembly, it eats all 3 of those tokens, right? So everything else about what you're doing better be like the most vanilla, repetitive thing that you've done a million times before, because you're going to be spending potentially all of your like innovation tokens, all of the time you have in your development budget for experimenting with new things, potentially like figuring out the tooling and ways of working and dealing with WebAssembly. So if everything else about your app is very simple, then yeah, you can experiment with this now. But the technology is maturing very rapidly, and so in the near future, you may want to be using or looking at WebAssembly if you have, as I mentioned, a problem with a distributed monolith, right? If you have that system where if you take out a single microservice, the whole thing collapses, you probably don't actually have microservices, and you really should be using a monolith. Secondly, if you're really worried about supply chain attacks, right? The micro sandboxing of the processes that you get, every single dependency getting its own sandbox is a really powerful result of that. And potentially, if you're sick of Kubernetes, you know, like Kubernetes is a very difficult job to manage. And if you could run WASM Cloud on like bare metal, or if it was a service just provided by your favorite cloud vendor, then maybe you could just be deploying components directly to that, and you don't have to deal with Kubernetes anymore. So yeah, thank you for coming and listening to my talk. That's all I have to say so far.